this is a lecture on indirect adaptive control of a robot manipulator. This is the fourth lecture in this module on neural control. The previous two classes we covered the background that are necessary to understand this lecture. First we talked about network inversion. Given a network that has learnt a dynamic model, can I use that network to compute what is input given a target output. The next one we talked about the problem of having a model of a robot manipulator. The reason is robot manipulator is an unstable open loop unstable system. Data generation can be only done using a PD controller. So, given those two background we will have this is the topics that we will be covering system identification using a feed forward network. This will be we have already discussed this, we will be overviewing neural network training and data insufficiency we have discussed earlier, query based learning. So, these are all from previous classes, and today we will be talking about two different indirect adaptive control schemes. One is based on forward inverse modeling and second is network inversion approach, and finally we will show these methods how they can be validated through simulation. So, robot manipulator, we have been talking about this model for since last two classes. So, this is a vector equation of motion of n-link rigid manipulator. So, this is the state space model. We have two n states, n angular position and angular velocity vector. Then the control vector is the joint torque actuated, which is n dimensional, and it is desired that the robot manipulator should follow this desired trajectory. We have already talked about given a generic system of this particular form, where this is our state output state. So, you can easily see for robot manipulator n is 2n and u is the dimension is p. So, this is a n state system small n. For robot manipulator will be 2 into capital N. The we collect the data online from a robot manipulator by taking the links, the manipulator link around the desired trajectory. So, we get various data from the robot manipulator. You use those data to model the robot manipulator in this particular form, which is x k plus 1 is f x k u k. So, you can easily see that this radial basis function network that has n plus p inputs x 1 to x n, u 1 to u p, and the outputs are x 1 to x n at sampling instant k plus 1, input are at sampling instant at k. So, these are the values taken from actual plant, these are the control action actuated. So, you get the output of the radial basis function network. So, if it is trained properly, then it can mimic the robot dynamic behavior. Okay. We last class also we talked about dimensionally insufficient data, which means since the robot manipulator is a open loop unstable system. So, we said that if this is my plant this is my robot manipulator. So, then I use a PD controller here, and I put some dither signal. And here is your command signal, right, and this is your sensor. So, the output of robot manipulator, if we actuate with joints. So, we observe what are the link angular positions vector and angular velocity vector. So, they are fed back at the command signal, and command signal is normally x desired, the desired trajectory that link should follow. You have this PD controller. So, PD output, we add this dither signal just to make sure that the data that are being collected not only spread over n dimension, rather n plus actually 2n plus p 2n plus p is also here n. So, actually given the state space model, we talked about n plus p. N is for x, p is for u. So, input output dimension is 2n plus p, because your input is number of input is n plus p, and that is when you have a network. If I have a network that has modeled this robot manipulator, then you have n plus p input, where n is capital 2n, n is capital 2n, and p is also capital N. So, that is 3n number of input, number of output is 2n, 2 capital N. So, the total input output dimension is 5n. Okay. So, the objective is to collect data in 5n dimension. So, to be able to do that is very difficult job, because we do not have a method by which we can independently give input signal to the plant or to the robot manipulator, which the input actuation cannot be made state independent, because we are using a PD controller. So, if I do not give dither signal, I am simply collecting data in only in n dimension. This n is actually 2n, and if I add dither signal, the maximum dimensionality into which the data will span is 2n plus n is 3n. So, 3n. So, this is the problem of dimensional insufficient data. That what is a neural network? Neural network means we are simply fitting the input data bit from input to output. So, it is simply a data mapping. So, how well data are generated. So, this point we discussed in the last class, and that is why we proposed a query based learning algorithm. In query based learning algorithm, what we proposed, that after the way we generated a data here, we generated data like this, and then we provided those data to the radial basis function network to emulate an actual robot manipulator. So, that first iteration robot emulator or neural emulator is placed in parallel to the robot manipulator, and then what this query based learning algorithm has to do is that it has to always ask this question, this neural emulator will be given new learning trajectories, and along each learning trajectory the through neural emulator the query through network inversion will be asked what would be the input for the desired target trajectory point defined by desired target point defined by learning trajectory. So, if and through network inversion we compute what should be the tau, we actuate that to the actual physical plant, and if we see the response of the physical plant in the next sampling instant is not the value is far away from the actual value of that is set as a according to the learning trajectory, then we accept that as a new example, because in that zone the neural emulator does not have proper information. What is the basic motivation here is that what we are saying, if I have a neural emulator that has modeled the robot manipulator, kindly hear very attentively this particular statement. What I am trying to say is that if this neural emulator or this the model of a robot manipulator, if it has actually trained properly to capture the dynamic behavior of the robot manipulator, it is not sufficient to simply say ask this question, given a desired sequence of desired input, if the neural emulator is able to follow the behavior of robot manipulator, then this is a proper emulator. No, we are going a step beyond. So, here what we are saying, the first step is that neural emulator should follow the behavior of robot manipulator. What does it mean, this first point? The first point means, given a sequence of control actuation to both robot manipulator as well as neural emulator, the response of neural emulator and robot manipulator, they should match. This is standard practice, but we are introducing a second constraint to say that the neural emulator actually emulating robot manipulator properly. What is this second point? Second point is that now we ask this question to neural emulator, given a target point, what should be the control input, and we give that control input to the actual robot manipulator, and we see if the manipulator goes to the target point. If that is the case, then we would say that the neural emulator is properly mimicking the robot manipulator. So, in this case neural emulator should using neural emulator, or let me properly say it, that using network inversion and neural emulator predict the control input for a given target trajectory. So, a control input sequence, I would say. So, this is the second point that we are imposing to say that a robot manipulator model in using neural network, how that can be robust. So, not only it should be able to predict what is the target point, it should be also predict what is the target input, because to this robot manipulator given tau it predicts q dot. So, one way we can say that if this is a neural emulator, give the same q dot to the neural emulator and tell him it should predict what is tau. The other way is that give the tau to the neural emulator and predict q dot, and we have to do now the both. If neural emulator satisfies the both condition, then we say this is an exact replica of the robot manipulator. Of course, we can't say exact replica, but in some sense it has a much more robust behavior than taking only this condition alone. So, we have already discussed these things. So, the control objective is, given a desired state trajectory vector, that is output activation of the radial basis function network model, which is xdk plus 1, and actual system state vector xk, design a controller so that neural model G is Lyapunov stable. So, what we are trying to say is that, now this is our robot manipulator, and this is our neural emulator that will mimics the robot manipulator behavior. Now, I utilize this neural manipulator and design a controller here, and this controller will actuate a control signal tau to the robot manipulator, and robot follows certain trajectory in the state space of angular position and angular velocity. So, this is called in literature, which we say indirect adaptive control. This is indirect adaptive control. So, what you are seeing here is that what is meaning of Lyapunov stable? Lyapunov stable is that if I represent this NE by a function G, okay. So, can I, because the normal stability study is that instead of robot manipulator, I can put instead of robot manipulator this NE there, neural emulator, and in feedback loop the controller and neural emulator in the feedback loop, they should be Lyapunov stable. Okay. So, that is the control objective. So, here the first type of indirect adaptive control scheme we will be discussing today. This is called forward inverse modeling. And this forward inverse modeling, what you are seeing here is that this is the robot manipulator. This is again in indirect adaptive control, you see, this is also indirect adaptive control, but the principle is forward inverse modeling. I will just explain to what is meaning of forward inverse modeling. This is our robot manipulator. This robot manipulator has a neural emulator. We have already discussed a lot about this, that what is a neural emulator. This neural emulator has the capacity to exactly mimic the behavior of the robot manipulator, not only in terms of what is the desired target, but given the desired target, what is the desired input. So, in both ways this is a very an ideal neural emulator, and then what we are trying to say is that this is our desired trajectory QD, this is our desired trajectory. So, given this desired trajectory, okay, here is my neural controller. See, I have two stage controller here. The neural controller actuates the feed forward torque, and the PD controller actuates feedback torque, and together they are actuated to robot manipulator together. The question that we are asking now here, that given a QD, you see that whatever the neural controller output and PD controller output, the same output is given to the neural emulator. Neural emulator gives an output Q hat, and we take that Q hat or the state compared with the desired trajectory, okay, and I get an error, and I use an weight update algorithm to update the weights of neural network, neural controller. So, what is meaning of forward inverse modeling is neural emulator is represents the forward dynamics of the robot manipulator. Okay. Now, what we can do, we extract from this neural emulator the information known as del x upon del u, which I will show you just now. This is a very important information that we get from neural emulator. We use that information which is necessary in our weight update rule to compute, which is w dot, okay. And we compute then update the weights of the neural controller based on this w dot. And what is this neural network controller? This is again another radial basis function network. So, we have two radial basis function network. One radial basis function network represents neural emulator, another radial basis function network is the neural controller. What we do not know in this radial basis function network, we fix the centers in their place in specific domain, because we know that to this controller what will be the various possible input, that is only QD, the trajectories, desired trajectory. So, actually to this neural controller we have 3 n inputs, n inputs from angular position, n input from angular velocity, and capital N input from angular acceleration. Okay. And then neural controller predicts what is the forward torque necessary for making the robot manipulator to exactly follow the trajectory. So, now we will show you how we we design a weight update rule for this forward inverse modeling, such that the controller the total feedback control system here is Lyapunov stable. So, how we are doing it, you see here, consider the Lyapunov function to be half x tilde transpose x tilde, where x tilde is x d minus x hat. So, this x hat is the response of the radial basis function network, which is here q hat. Okay. The time derivative of the Lyapunov function can be derived as follows: v dot rate derivative is x tilde transpose into x tilde dot, okay, x tilde dot, and then we can write that x tilde transpose, then we can write that del x upon del u, because you see that this x tilde dot is x minus x hat dot. Okay. So, that is minus dx hat by dt. So, dx hat by dt can be written as dou x upon dou u into dou u upon dou w into dou w by dw by dt. So, that is this we are expanding that x is a function of u, the control input, u is a function of w, and w is a function of time. So, if you go back here, this is the meaning of forward inverse modeling, that is, given x hat here, this is a function of u here. Okay. So, that is why dou x upon dou u is computed from the neural emulator. Okay. Again the neural controller output is u, we can say the output is here is u. So, dou u, so dou x upon dou u into dou u upon dou w, that again can be computed from this neural controller into w dot is what is dx upon dt, dx upon dt. So, I have to explain to you again. What we are trying to compute is dx upon dt. So, to compute dx upon dt, which is x hat, that is the rate change of the output of the neural emulator, is can be written as dou x upon dou u, okay, into because this neural emulator has a functionality relation between q and u. Again dou x upon dou u, here it is dou u upon dou w. So, the neural controller is characterized by a weight vector w, and this u, output neural controller, is a function of this w. This is not a, because PD controller gains are fixed. So, this has no this really do not affect this q hat. What affects is the weights, because these are changing neural controller. So, dou x upon dou u, again dou u upon dou w. So, u is the output of the neural controller. Neural controller is characterized by the parameter w, and the input is q d, which are all known. So, naturally dou u upon dou w can be easily computed from the neural controller into dw by dt. So, this is the weight update law. So, now we have to find out what should be this dw by dt, such that the whole system is Lyapunov stable. So, meaning of that is that Lyapunov stable means, if I consider this to be a Lyapunov function, the rate derivative of this function v dot has to be negative definite. If I can prove that this is negative definite, then this is a stable controller. So, the objective is to, here I have defined j to be this quantity, this is j, Jacobian. The objective is to select a weight update law w dot, such that the derivative of the Lyapunov function remains negative semi definite. We will now represent two such weight update laws that are converging in the sense of Lyapunov function. So, we are selecting first what is w dot, and this is the my w dot, the weight update law. If I select this weight update law and put this weight update law in this particular replace here, then what I get, b dot is minus x tilde norm square. So, meaning this quantity, this particular quantity is either, if it x tilde is not 0, then it is positive, hence it is negative, and if it is x tilde is 0, all the terms in x tilde, because this is a vector, if all the terms are 0, then only at that time it is 0, which is desired, x tilde finally should be 0. So, that is desired. So, then the system is stable. So, thus the update law, the previous law that what we saw. So, that this, so what we showed, this stabilizes the control system. The complete control system, including the plant dynamics, is stable according to this weight update law. Now, the weight update law, however, does not ensure the boundedness of the weight, because you see that we are updating this weight, and there is no way we are talking about boundedness of the weight. So, that we will be doing now. So, thus the update law is modified by adding a gradient of the cost function h as follows. So, w dot earlier term was this one, we have added another term where we have taken a gradient of a function h, okay, and this h is normally, we select here, you can check here, this is half w transpose tilde into w tilde. So, taking this h to be this particular function, so del h upon del w, if you compute that, and where this particular function that you are looking at, which is a function of w, is defined by this quantity. So, if you take that add this term to this w dot, then again you take this new weight update law into the rate derivative of the gradient Lyapunov function, then Lyapunov function again becomes x tilde norm square negative of x tilde norm square, implying again the system is stable. So, again this control law stabilizes the control system in the sense of Lyapunov. So, the system is Lyapunov stable. So, finally, this update law ensures convergence of tracking error vector x tilde to 0. A new function is chosen such that x transpose j this function is 0, which ensures the time derivative of the Lyapunov function remains negative semi definite. Simultaneously, by selecting h to be half w tilde transpose w tilde, we are intuitively providing a damping to the weight that is increasing. This ensures the boundedness of the weight vector w. So, finally, summarize, two weight update rules are derived which guarantee stability for forward inverse modeling based indirect adaptive control. Weight update rule 1 was w dot is this this is this is how. So, if I go back, what was the problem originally? Originally the problem was that we place a neural controller whose weights are unknown. How do we update these weights such that the overall the control system is stable and the perfect tracking is achieved at the plant level. So, that is what we are doing. First is we found out the weight update law for the weights of the neural controller. So, weight update law, this is for the neural controller. Similarly, weight update law, second neural update law we found out. So, this does not take into account of the boundedness of the weights, this does take into account. Now, we will go to the second approach, that is using network inversion. So, we have already talked about network inversion. So, now the concept here is very simple. I have a robot manipulator, I have a neural emulator. Now, can I use this neural emulator as a whole to construct my control law here that would stabilize the entire control system here? That is the question. So, that is what I am trying to say is that if I have a controller here sitting here in conjunction with the neural emulator, can I say given a desired trajectory here which I have it is here next desired state, present and past states and past input, or you can always also say here that q d given a desired trajectory, can I say that I have a control law in conjunction with the neural emulator in such a way that finally my the neural emulator output are always following the desired trajectory and system is Lyapunov stable. So, this is the network inversion. So, control law using network inversion. So, what we are trying to do, we are constructing a Lyapunov function which is half x tilde transpose x tilde plus u tilde transpose u tilde. So, we have introduced a new element or new term in the Lyapunov function, where u tilde is u hat minus u. What is this u hat? If you go back, you see that when I invert the network, I get what should be the control input that will take my neural emulator to the target vector. So, you know already that there may be a situation where my predicted control input may not take the robot manipulator to its actual target, because of the problem that we enumerated in the beginning, that actual neural emulator is that one which not only predicts the target, also predicts the desired input. And if that training is not complete, then obviously the neural emulator will fail sometime to predict the control input. Now, we have to find some method by which that this prediction can be made proper. So, with this introduction of this new term, we take the time derivative of the Lyapunov function, and then you will see that if I differentiate this term x tilde transpose x tilde dot, and x tilde dot can be written as minus dou x upon dou u. So, that is why the minus sign comes into dou u by dt. So, du by dt. So, that is how this first term. Second term is u tilde transpose into u dot. Okay. The and where we can write this term as minus x tilde transpose j plus d u dot, where j is dou x upon dou u and d is 1 upon x tilde norm square x tilde u tilde transpose. So, control using network inversion. This is we first of all we present a theorem. If an arbitrary initial input activation u naught is updated by this formula, this identity u t is u naught plus 0 to t dash u dot dt, where u dot is given by this expression, then x tilde converges to 0 under the condition that u dot exists along the convergence trajectory. Substituting u dot in v dot, u dot in the previous v dot, you get v dot is minus x tilde whole square, again which shows that is the overall system will be Lyapunov stable. The iterative input activation update rule would be, because this is continuous update. So, iterative will be u t is u t minus 1 mu u dot t minus 1. This is iterative actually, because t we have given in terms of time, maybe we can put it this is k, where m is a small constant representing the update rate, okay, and where u dot is computed from this expression at the sampling instant k minus 1. We propose two different control indirect adaptive control schemes, and we found out the control law and weight update law for a specific another the first case we found out the what should be the weight update law for the controller. In the second case we found out what is the control law, and now we will show that how this controller are effective. So, we selected a high speed robot manipulator whose dynamics are given this way, where in this particular dynamic model C T 1 stands for cos q 2 minus q 1 and S 2 1 stands for sin q 2 minus q 1, this two link manipulator. And the parameters a 1, a 3, a 4 and a 2 they are 0.15, 0.04, 0.03, 0.025 kg meter square respectively. We have selected the same robot manipulator that we have been discussing in the last two classes. The online data generation scheme for training the radial basis function network is the same. A PD controller is used to generate the training data to find a neural model of the robot arm. Data are collected as the robot arm is made to track various random pick and place trajectories and sinusoid trajectories. While tracking random trajectories at each sampling instant, various dither signals in the form of white noise, impulses, step functions, ramp and parabolic type of functions are added to PD controller to increase the spread of the training data in the input output space. This is from now we shift the data from n manifold to n plus p manifold. 3000 examples are collected where the sampling interval is kept at 10 millisecond. And then radial basis function network, which has 6 input, that is 2 term for joint input, 2 terms for angular position, 2 terms for angular velocity at sampling instant k. When you give to the network will predict what should be the actual value of the angular position and angular velocity at k plus 1. The model incorporates 100 radial centers. Training of RBFN is carried out using 3000 examples for 10 number of passes, that means 30,000 iterations. After training is over, the RMS error for a test data set is found to be 0.003. The validation test of neural model thus learned is done by finding input through recall process for a given test data. It is not simply because when you have the RMS error 0.003, then you can easily see that easily can predict the output, the radial basis function network will effectively predict what should be the output given an input. But what is the case given an output, can the same network predict what is the input? So, this one also, this results we showed the last class. So, this is for a sinusoid trajectory. When robot manipulator is tracking a sinusoid trajectory, we ask the question to the robot, the neural emulator corresponding to the robot manipulator, what is the input given the target output. So, that input is already given to the robot manipulator. So, what this result is all about is, I can tell you again, this is my robot manipulator and this is my neural emulator. So, this is my U, I give to the robot manipulator and I get Q. I give that same Q to the neural emulator and predict what should be that U. So, if this U hat matches this U, then this neural emulator is a good emulator of the robot manipulator. I hope you understand very clearly. Again I repeat, what is meaning of this validation through inversion? Validation through inversion means of course, we have trained this neural emulator by giving the training set U and Q to this NE. So, obviously, if I give U, this will predict what is Q, but given Q, can I predict the U? This is the question we are tying. So, the both way the neural emulator should do a perfect job, then it is a robust identifier, a robust model of the actual robot manipulator. So, what you are seeing is that we have already discussed in the last class that before the query based learning that we discussed today, also yesterday, that before query based learning the input prediction was very bad. You see that these are lot of variation from the solid line. Solid line is the actual control input that is given to the robot arm for a desired sinusoid trajectory. But after query based learning for the joint one, you see that the predicted one, the broken one and the solid one, they are almost very close, where the dotted one, this is before query based learning. So, after query based learning the model has become very robust. So, not only the neural emulator is predicting the target given input, it is also predicting what should be the input given the target, and the same thing also valid for the joint 2. You see the before query based learning, again you see these dotted lines, they were not good, they were not similar to the actual the solid line, that is the control signal sequence given to the actual robot manipulator. But after query based learning, you see that this broken line almost follows the solid line. So, this is the advantage. So, this is the neural emulator we have now utilized for testing our controller. I will not discuss, because these things we have already talked in the last class. So, we will now show the simulation result for the two control algorithms that we derived today. To repeat you for your own understanding, we first of all propose a forward inverse modeling. In forward inverse modeling, this is my robot manipulator, this is my neural controller. Okay. So, neural controller is supposed to actuate a a feed forward torque and such that the Q tracks QD, Q the output of the manipulator tracks QD. So, the neural controller is a radial basis function network whose W is not known. Now, how do I update this W in such a manner that my the Q follows QD, and this is Lyapunov stable. So, for that, as you saw that today in this class we derived a weight update law called W dot, okay. And this W dot is computed by using two terms. First term del dou x upon dou u is computed from the neural emulator. Another term we computed this term dou u upon dou w from the neural controller itself. Using these two, we computed what is W dot, okay. And this W dot in the first case, this was x tilde norm square upon J transpose x tilde norm square into J transpose x tilde. And the second rule that we saw, that we added a gradient term of the weight where h is half W transpose W. When we took this value for h and we differentiated that, then we found that this weight update rule also Lyapunov stable, this weight update rule also Lyapunov stable, or gives us Lyapunov stability. And using these two rules, we did simulation. This is forward inverse modeling simulation. What you are seeing is that we provide the robot manipulator the same trajectory for 50 times. Okay. So, we start here what we started with. We started with in this neural controller, the weights are all initially randomly initialized, we did not know. Now, with this initial random weight, we used various algorithms. First is gradient descent. So, what we did is that we simply updated the weight according to the gradient descent, and you see the over 50 trials, the error in joint 1 position is, this is trial 1, this is the RMS error, and slowly the RMS error reduced and it is here. But when we use the gradient descent, but with weight update thrice per sampling interval, then you see that error further decreased. And then the third one is the adaptive tuning, that the first we have two update rule, the first type of update rule. So, you can easily see this is the upper one, and then you have this the same adaptive tuning algorithm, but weight update thrice per sampling interval. Then you see that it is further improved, but you see the amazing aspect of the adaptive tuning, that is the type 2. So, when you do the type 2, you see that error is actually almost 0 and independent of trial, it does not require any trial, that is instantaneously the error goes to 0.000001. Okay. This is a very fantastic performance of this controller. The the controller that we talked, this type 2. So, type 2, you see the type 2 controller, here also the error is on the x axis, means 0.000001. So, here also you see joint 1 velocity, the error is very small, and here also the error is very small, whereas other schemes they have relatively large errors. So, we compared. Now, we will take an example here. This is the sinusoid trajectory that is being tracked by this robot manipulator. This is joint 1 angle, and you can easily see in the beginning there was some error, and that error died down as time progressed. And you can easily see there are two, this is the tracking error, this is the trajectory tracking, this is the tracking error at joint 1. So, this is this solid line is using the new update rule, and whereas the dotted one is using gradient descent. So, similarly here on joint 2 the tracking is very perfect, and whereas because you can't even see the two trajectory, the actual trajectory and the desired trajectory, they are superimposing so perfectly that they appear to be the same trajectory. So, tracking is perfect, and a tracking error at joint 2, if we see in a very micro scale, then you see that for gradient descent the error is quite visible, whereas this is almost 0 for the adaptive tuning that we have done using Lyapunov stability theory. So, that is a simulation result of the first part. The second part is a network inversion. In network inversion, what we did is that we have already a neural network. We said, why should we put another neural network there? Instead, we have a neural network that has already identified the model of the robot manipulator. We utilize that neural network to predict what is our control law, such that the overall the system is Lyapunov stable. So, what should be the control input u dot here, or the u here, what do we say, this is my u or tau. So, that will be a function of u hat that has been inverted, that is the that is given from the network inversion algorithm, and j is the Jacobian that is computed from the neural emulator, okay, that is del x upon del u. So, we have this we derived this algorithm. My control algorithm is ut, u is same as tau, is ut minus 1 mu u dot, and where u dot is this expression which can be computed very easily because these are simply norm square. J is a Jacobian matrix computed from the neural emulator. D is an expression that we already expressed in our in this class. So, when you implement this thing, then you see that here what you are seeing is that we have two robot manipulator. This is joint 1 and this is joint 2. So, the A is tracking error in joint 1 and joint 2 using control law for sinusoid trajectory after query based learning and before query based learning, and controller response, okay, this is the controller response, okay, controller response for joint 1 and joint 2 corresponding to figure, okay. So, this is the controller response, this is tracking error, and this is u. So, this curve gives you u. So, you see that this dotted line what you are seeing here, this is the control action before query based learning we implemented. So, you implement this network inversion control before query based learning, So, this is you see that controller is fluctuating, but as soon as you did the query based learning, then the controller is smooth, the solid line. So, correspondingly when the controller was not smooth, the error was very large, but when the controller becomes smooth, the error is almost very negligible in joint 1. Similar the case with the joint 2, you see that the controller is fluctuating here, quite very much fluctuating before query based learning, and that means when not a properly trained neural network is used, then we have a large error. But when the query based learning was completed, we again implemented the controller. So, you see that the torque is very smooth here and the error is very small. The similar thing here, that in this case this is that is the previous one is a sinusoid trajectory, this is exponential trajectory. So, for the exponential trajectory you see that this fluctuation is due to before query based learning, and fluctuation die down when I am using the after I am implementing the controller after the query based learning. So, that is the solid line that is quite smooth, and corresponding to solid line, the solid curve here implies the error in joint 1 tracking is almost negligible, not there, whereas without query based learning the error is there, always existing. Similarly, joint 2 with query based learning, this is a solid line, almost no error, and error is there before query based learning, and you can see this fluctuation here that indicates the that controller is control actuation is not smooth. So, in summary, indirect adaptive control for a robot manipulator we discussed today. This indirect adaptive control has two different architecture we proposed. One is indirect adaptive control using forward inverse modeling approach, another is indirect adaptive control using network inversion. We say these are indirect adaptive control because we are utilizing the neural emulator, the forward modeling, that is the forward dynamic model. We train a neural network that captures the forward dynamics of the robot manipulator, and utilize that neural network to tune our controller or to update our control law. Both the control schemes are shown to be Lyapunov stable. Simulation results are provided to validate efficacy of the proposed schemes. We saw that how our tracking is almost perfect when we have the neural emulator that is perfectly trained using query based learning, and then we implement this controller, the results is fantastic. So, those who want to pursue further work in this the last 3 classes, they are kind of one in a box type of course. You can follow this these references that we have given here for further work. First one is our own paper that is published in 2003 in Computers and Electrical Engineering Journal. This is the second one is again our paper published in IEEE Transaction Neural Network in 1996. This is volume 7 number 6. The third paper is again our paper, is IEEE Proceedings Control Theory Application in 1995, volume 142 number 6. This is another paper that is called Inverting Feed Forward Neural Networks Using Linear and Nonlinear Programming by Bao Liang, Lu and Kita, H Kita and Y Nishikawa. This is in IEEE Transaction Neural Networks, volume 10 issue 6. And another one is a query based learning for aerospace applications, that is their IEEE Transaction and Neural Networks, volume 14 issue 6 November 2003. So, that should give you a good exposure how to design indirect adaptive control schemes for robot manipulators in particular and in general for nonlinear systems. Thank you.